Hello, this is Designing the Architecture from Team Jefferson with Luis Castro, Mihail Kaburis, Maria Ochoa, and Jude Simonis. So first we're going to talk about what is design. In previous presentations, we've already discussed understanding our customer's problem, the requirement specification that describes what an acceptable solution is, and that focused on function and guided us on how to build the system. But when we talk about design, design is the creative process of figuring out how to implement all of the customer's requirements. And the resulting plan is also called design. In the early design decisions, we're trying to address the system's architecture. So we may break the system into units and explain how those units relate to one another, and then describe the individual visual properties of those units. These things can be difficult to change. In later design decisions, we're going to address how to implement the individual units. And these things can be relatively simple to change. As an example of this type of analogy with architectural plans, we can talk about how you're given the following specifications from a customer. 3-bedroom and 2-bath location, place for the children to play, a kitchen and a large dining room, storage for bikes, furniture, etc., and an HVAC unit. And that's what the customer wants from the architect. So the architecture is going to include things like the routing for heating and cooling, the water piping, and the electrical wiring. These things are pretty difficult to change, but they can be done if the need is present. But later changes, things like changing the floor, the cabinets in the kitchen, or the paint on the walls, they're pretty easy to make. So getting feedback from customers is pretty important, and that's really part of that later design process, but also the early design process as well. Design is really difficult. Usually there's going to be some sort of exceptional cases where we're missing or we're not given the right information that we have to accommodate in the system. There may be some non-functional design goals like maintainability, ease of use, porting to other platforms, and these things may even conflict with each other. And there's even external factors like being compatible with legacy software, utilizing pre-existing hardware specifications, government regulations, etc. So there's no easy road to success. It's really the creativity, intelligence, experience, and expert judgment that are needed to design a product that's adequately going to solve what the system requirements are from the client. Most design work is routine design, in which we're solving problems by reusing and adapting solutions from similar problems. So it's pretty important that we improvise. So most experienced software developers rarely design new software from the ground up. Instead, they borrow ideas from existing project solutions and manipulate them into new, but not entirely original designs. By doing this, developers are able to arrive at a suitable design much more quickly. This diagram here really represents that process, so we see things like similar systems, reference models, architectural styles, design patterns, design conventions, principles, and experience. And these things really help accelerate that design process. There's two main types of designs that we're focusing on in this course. And these are conceptual and technical designs. So in software engineering, a conceptual design has two critical purposes. One is to conceptualize the software, provide a broad outline of the function and form. Also conceptual modeling, so you want to invent or at least recognize the software's behavior. On the other hand, technical design focuses on how abstractions can be represented as data structures, modules, etc. A good point to bring out is, which one do you focus on first, the conceptual design or the technical design? In many cases, you may want to start with the technical design, even though it sounds a little bit less obvious than starting with the conceptual design because that's easier. When you have your data structures and you have all of these tools ready, you have something to present to the customer that's an actual product instead of just drawings or concepts. And that's going to make you as the designer much more successful when trying to work on new projects and gain trustworthiness with customers. So an example of good conceptual design, at least from the point of view of a engineer or developer, would be something like the document or these images on the side here, which are adapted from Daniel Jackson's Towards a Theory of Conceptual Design for Software. At the top, in Figure 2, we see a conceptless state transition diagram for a timer. If we were just given this, I mean, this would not be enough to tell us what the system's doing. But if we were given the schedule concept in Figure 3, now we have a better idea of what's going on. But if we were to give this to a customer, instead of just a group of software engineers or just general engineers, if we're building a system that maybe uses this for a factory or something like that, we may be confusing the customer. So we would probably want to use even clearer diagrams, things that are more like flowcharts and things that kind of abstract the higher technical details to really give the customer a picture of a more broader approach of what we're doing. An example of great technical design is the car analogy found, especially when we're talking about abstract data types or ADTs in data structures. So when we think of things like a steering wheel, the brake, the clutch, or the accelerator in a car, we have an idea of how those things work, right? We have the interface. You know that the brake's going to slow down the car. We know that the steering wheel is going to turn the car, etc., etc. But how those things run, the implementation, whether we use a V4 or a V6 engine, that matters, especially for developers, right? Our algorithms, the type of data structures we use are going to change that time-space complexity quite a bit. So having a great technical design, that can make all the difference, especially when we're dealing with huge data sets, which many companies in industry are. So it's really important that we look at these things. So there are many ways to leverage existing design. One common way is cloning, where we borrow the whole design. Essentially, we copy and paste it and make some minor adjustments to fit our own code. Another way is the reference model, which is almost a standard template architecture for a particular application. And that's where it's going to suggest only how we decompose our system into its major components and how those components interact with each other. We can see an example here with the compiler, a reference model for that. And we see all the parts, but this may only be useful for the compiler. And that's because most systems don't necessarily have a reference model, so we have to adapt a generic design solution. And we do this through things like data structures and, of course, algorithm paradigms like divide and conquer and dynamic programming. Software architects utilize many architectural styles, and these are similar to reference models in that they decompose software problems into units and tell us how those units should interact with one another. But unlike reference models, they aren't optimized for specific application design. They give general advice about how to approach design problems. And good design focuses on selecting, adapting, and integrating several architectural styles to produce a desired result. Some additional terminology are things like design patterns, which are just generic solutions for making lower level design decisions about individual software modules or small collections of modules. Then we have things like design conventions and idioms. And these are things that are essentially taken together. They'll promote certain design qualities. Innovative design, which is a regular burst of progress, which I'm sure many of us have had. And, these are used when we can't find an existing solution. And, a set of design principles will be used, and these are really important in major companies. Something that we do follow is the design process model, which design is an iterative process. So developers are always moving back and forth between understanding the requirements, proposing solutions, assessing feasibility of various parts, presenting options to customers, and documenting design for customers. The end result of this is the software architecture document, or the SAD. And sometimes this conflicts with the agile goal of avoiding irreversible decisions, because the SAD is really kind of saying, hey, this is what it is. These are hard to change things. And Agile is like, but we can be flexible. So that can be a little bit troubling. So David Garland, who's a professor at Carnegie Mellon, and he specializes in software architecture, talks about the 6 bare minimum ways that we can use software models. To understand the system, to determine the amount of reuse from other systems and the reusability of the system being designed, to provide blueprint for system construction, to reason how the system might evolve, to analyze dependencies, to support management decisions and understand risks. There are many ways to model these things, like UML diagrams, or we can even go back to the basics of simple box and arrow diagrams. It's really important that we realize that these are just the bare minimum and that there are so many more things that one can do to build or utilize software models. So decomposition. Essentially, decomposition is a tool that was originally used for making a large problem more tractable by decomposing it into smaller pieces whose goals were easier to address. So this was like a top-down approach, as we can see in the diagram. So we start with that big picture and then break it down. But today, most designers are taking a bottom-up approach on architecture packaging by taking these smaller components and building that larger whole. Some experts say that this makes systems more easier to maintain. So Anthony Wasserman, who we've talked about previously in the course, describes 5 ways we can partition the system into modules. And again, this is not an all-inclusive list. These are just 5 ways. So we have modular decomposition, which is based on assigning functions to modules. Data-oriented decomposition, which is based on external data structures. Event-oriented decomposition, based on events that the system must handle. Outside-in design, based on user inputs to the system. And object-oriented design, which is based on identifying classes of objects and their interrelationships. The method we choose depends on the type of system we are developing. So software unit is usually utilized to talk about a system's composite parts without being precise about what type of part. There are several different types of software units. We have components, subsystems, runtime processes, modules, classes, packages, and libraries. And they all are of different sizes, and they help us visualize and package the different parts. So a design is modular when each activity of the system is performed by exactly one software unit, and when the inputs and outputs of each software unit are well defined. A software unit is well defined if its interface accurately and precisely specifies the unit's externally visible behavior. Each specified input is essential to the unit's function, and each specified output is a possible result of the unit's actions. The interface says nothing about any property or design detail that cannot be discerned outside of the software unit. So we have this huge component, and everything's included inside that we need for that unit and subsystems. So moving along to architectural styles, there are 3 main levels of design. So we have things like architectural design, which is the highest abstract version of the system, higher level design, which is less abstracted views of systems and modules, and then we have detailed low level design, which is essentially additional breakdown. And we talk about how the modules communicate with each other. A great example of this would be maybe like a car sales program that we could be building that tells us how many cars we have in inventory. At the lower level, maybe we have some sort of validation system for a login. So it's checking if the password is the right length, etc., or has the right amount of characters. And then at a higher level, maybe we have the entire how the login system is working, so how it's validating, etc., what it's doing. Maybe it's sending something back and forth between the database. And then at the architectural design, we have everything in the project, everything in the program, including all of the bigger components like checking the actual inventory. So one way of representing top-down design is creating a software architectural design. So creating a software architectural design is not a linear task. design teams often switch between top-down and bottom-top analyses depending on the type of project that they're working on. So top-down is when we're going to partition the system's key function into distinct modules that can be assigned to separate components, and then bottom-top is when we are adapting a prepackaged solution. There are a variety of architectural styles, and these are large-scale patterns of system structure. Just like architectural styles for building, software architectural styles have defining rules, elements, and techniques that result in designs with recognizable structures and properties. They're loose templates that offer solutions for coordinating. Style catalogs are available, and these are tools that architects can reference when looking for general designs. And we'll talk about some of these general designs right now. So one really common design is the pipe and filter style. So filters input data passed through a sequence of data transforming components, and pipes are the connectors that simply transmit data from one filter to the next without modifying the data. I think the diagram below does a great job in describing how that works. Also, the program above is from Ramda in JavaScript, and it shows you how a pipe function works when you give it the numbers 3 and 4, and then process it through math.pow, r.negate, and r.increment. There's also object-oriented design. So this is a design paradigm based off of dividing the responsibilities of a system into individual reusable and self-sufficient objects. High-level design identifies the system's object types and explains how objects are related to one another, and then the lower-level design details the object's attributes and operations. So here with this UML diagram, we see a high-level design, but if we wanted a lower-level design, we could look and see what's inside something like display average student or ID exists and learn how that works. There's also the publish subscribe style, and this is where components interact by broadcasting and reacting to events. A component expresses its interest in an event by subscribing to it. When another component publishes that the event has taken place, the subscribing components are notified. Implicit invocation is a very common form of the public subscribe, where a subscribing component associates one of its procedures with each event of interest, and this is called registering the procedure. So an example of this is callbacks. These are pretty common in JavaScript. In a project I'm working on right now, for instance, we're using callbacks to get the username before connecting to the server. Another common architectural style is layering. Layered systems organize the system's software units into layers, each of which provides services to the layer above it and act as a client to the layer below it. So typically, software units in a given layer can only access other units in the same layer and services offered by the layer immediately below it. But layer bridging allows us to access the services of layers below its lower neighbor. So this provides a high level of abstraction, but it's not always easy to structure, and it may lead to a decline in system performance. So for instance, if we want to build a network, we can access data and the physical, so the lower level types of components as well to do so. Repository is another architectural style, and it consists of two types of components. There's a central data store, and then there's associated data accessing components. In a traditional database, data store acts like a server component, and the data accessing clients request information from the data store, perform calculations, and request that results be written back to the data store. Data accessing components are active in that they initiate the system's computations. A Blackboard repository, on the other hand, utilizes knowledge sources, and these contain information about the current state of the system's execution that triggers the execution of individual data accessors. The data accessing components are reactive. They execute in reaction to the current contents of the data store. And I think we can see that with the typical Blackboard. So knowledge source 1 may lead to a chain reaction and open up knowledge source 2, etc. Interpreters. So these are programs that translate code from high-level programming languages into machine code or instructions understood by the computer. Most of us have used these, and we've at least used one interpreted language like Python, Ruby, or JavaScript. Unlike a compiler, input is analyzed piece by piece, right? So the entire program isn't being read and then telling us what's going wrong. It's literally every part is being read, and if there's a problem, the interpreter will let us know immediately. These are incredibly versatile, but they can be slow and difficult to design. So unlike compiled languages like C, C++, and Java, there's less pre-processing and more just let's get directly to that low-level code from the higher-level language. Compilers are going to make like an object code with all sorts of data and then go ahead and do some stuff and make things a lot more complicated, but sometimes that can be useful depending on the type of environment that we're looking to build. Process control is another very important topic. So when a computer is used to automate and regulate the operations of a system, computer-aided industrial processes are a very, very common thing in industry. And they're very risky, though. We need to be careful because these go into things like pharmacology, nuclear reactors, etc. If you make a mistake in these fields, like you add 0.01 milligrams extra of a dosage of maybe morphine, you could have an issue with the type of drug that you're producing. So it's absolutely essential that things are produced to the exact scale. These can get extremely complicated due to corporate demands, government regulations, etc.
Alright guys, so we're going to take you through these slides. I'm Jude, and this is abstraction. So basically, abstraction is a way to generalize the process and you remove the details of the system so that you can focus on another system. So for example, we have the OSI model here. Pretty much look at someone who's designing a software for the application layer. Without abstraction, they would have to know what each of these layers are doing under here, and that's just unrealistic. So with abstraction, the software designer would only need to know that, hey, the presentation layer is going to provide me these services, and it's what each layer is doing. They don't necessarily need to know the intrinsics of each other layer. So that's pretty much abstraction. Here I have some more examples of abstraction, where this is basically, I think that abstraction can start off with just how you name your functions or name your variables in code. So none of these functions, you can see what they do, but because of their names, you can easily probably know what they do. And assuming that the functions are written correctly, that the service that their names are telling you that they provide will be provided when you run these functions, assuming you put the proper parameters for whatever you're trying to do. So modularity, what is modularity? That's pretty much imagine like puzzle pieces where the puzzle as a whole is your system, and the pieces are the divisions of your system. So each puzzle piece has its own function, and they can all integrate with each other, and together they all form a system. So you want to aim for as much modularity as possible. It helps you debug your code easier because you can focus on where the problem is, instead of like having one big main function where the problem can be anywhere. So how do we build modularity in our software? Well, to do that, we need to decompose the software, and we have some various methods that allow us to do that. We have functional decomposition, where you divide the main functions into subfunctions, and the subfunctions into more subfunctions. You have feature-oriented design, where you divide the main features into modules, and you describe how each feature affects the system and how they interact with each other. This is very similar to functional decomposition. You have data-oriented design, where you partition data into modules by providing conceptual data structures for the job at the high level and the low level, detailing how the data realizes the conceptual models. So yeah, you're just seeing all the different types of data you have, and you're gonna give them you're going to divide the program into modules based off of the data that you have and, you know, what data structures you're going to use. So we're describing more. We have a process-oriented decomposition. This is where you have you list the main tasks of your system, and you're gonna divide the system into modules based off of subtasks, and you're gonna divide those subtasks even into more subtasks. And at the low level, you're pretty much gonna describe the processes in detail. With event-oriented decomposition, you want to look at the events that your system has. You know, the user inputs that it can accept and all that stuff. And you're gonna divide the system based on off of the events that it can take. And at the low level, you're gonna decompose the system into states and explain how the system changes states. With object oriented is pretty much the most simplest one. You just list all the objects, and you're gonna basically decompose or just describe the system in terms of objects. And you know, at the low level, you can describe the attributes of these objects and how they relate to other objects. So here we're talking about collaborative design, which is a team. Well, this one's team-based design, and designing as a team, it can be really good for your product, but it's only good if you guys are all on the same page and you guys are actually working together. Because you know, I heard this one quote once that was pretty funny. It was like, you know, what one developer can finish in 1 week, 2 developers can finish in 2, which that can be a very true statement. So to ensure that your team-based designing is being efficient, you kind of want to follow these bullet points here. Not necessarily to the T, but you know, they're pretty important. So you know, every person on the design team has to be on the same page. Work needs to be divided in such a way that the best people for the job are working on said job. The documentation is in such a way that everyone on the team can understand it, and every subunit that the team creates can integrate smoothly with other subunits and use the... wonder where that went. Also, everyone needs to be aware of the causes of software breakdown and use team strengths to avoid it. So here we also have the causes of design breakdown. This is what's mentioned here. This is written by Gwendon, Krasner, and Curtis. You want to make sure that basically that everyone can assure that these things, that everyone knows that these things are something that can cause design breakdown. Some of them involve, you know, a lack of specialized data schemas or poor prioritization of issues. So you just want to make sure that your team is aware of how things can go wrong. So outsourcing is a type of distributed development. It's a way to cut costs and improve productivity. Work may be sent to other companies or divisions, and these companies may be located in other countries. So generally, when you're outsourcing, what happens is your on-site team makes a project, and your on-site analysis researches the requirements of the project, and they send those to the outsourcing team. Then the off-site team is going to build the generic products / components to be used for pretty much any on-site facility, so it's like worldwide. Finally, the off-site team they'll get better at what they do, and they'll start building products that specialize in their expertise. So, you know, that's where they get their leverage. The problem with outsourcing is communication, culture, and work style. You know, if you're outsourcing close to you, then, you know, communication is not going to be that much of a problem. But, you know, the farther you outsource, the bigger there's going to be a communication gap. You know, people might talk different languages. And, you know, when you describe them your stuff, you're going to have to find a way to describe them in such a way that it's left to zero interpretation, that, you know, that they understand what you're talking about. You also have cultures. Some areas focus, they build their stuff different ways because of their culture. So you want to make sure that you know, that they're building it for your culture and not theirs. And work style, pretty much, you know, other countries may work differently, and, you know, there's also time zones you have to worry about. You just gotta know, you know, who you're working with and how to work with them. So here we have a user interface. User interface pretty much should be its own software unit. It allows for easy customization and fitting for various cultures if you make it its own software unit. So you can just like plug in the parts you need to change if it's its own unit. You know, your interface should also support handling events that can be sent by the user at any time. So, you know, we can know, like, we can have a text box. We can know that the user is going to interact with that with listeners and stuff. But you also have to be ready for the things that the user can change anytime, like trying to go back, using undo, stretching the screen, using multiple views. You got to make sure that those things are kind of unpredictable. So you need to know that your interface is ready to handle those events. Now, user interfaces are important, really important, because the customers or the users, they're going to be ones who are looking at that. And you can have the most amazing program ever, but if the user interface sucks, no one's going to want to use it. So we have to try and make it as frustration free as possible. So interfaces also should probably be aware of themselves. If you have any events that are time related or notifications, then there has to be some internal awareness for that interface to know, hey, I have to trigger some time sensitive self routines that are part of it. So basically your interface needs to know in itself how it's working so that it can trigger these things properly. Here we talk about concurrency, and concurrency basically comes down to synchronization, which means the cause to occur or operate at the same time. And we can show this in code by using like semaphores, locks, and mutual exclusion. So here's some code I've had here from when I was in my OS class, and this is like a producer-consumer problem. And basically you don't want the producer to be producing something at the same time the consumer is consuming something. So you have some semaphore waits, you have the mutex, and you have full, and you have the signal, post, and wait. So you want to make sure that they're communicating with each other, so that at any given point only one of these things is accessing the buffer. So that's why we call that mutual exclusion. So basically we have different methods of concurrency. You can use threads or multiprocessing. So threads are faster, they're less expensive, they live in the same area of memory as the main thread, and you can accidentally overwrite the work of other threads because of that. So when you create threads, they're all part of the main program. So that they're all in the same area of memory. So you have to make sure that threads don't write over each other's memories. Then you have multiprocessing, which is slower than threads. You have to create like a new program in memory, and it's harder to share data between processes because they're in different areas of memory. You also it's also when you it's faster to switch between threads because threads are all in the same program. But with processes, since they're two different processes, to switch between them, that would involve stopping one process, saving its state, and then switching to the next process. So overall, for most cases, threads would probably be better to use. If you want to like assert like priority, some languages like Java, you're able to set thread priority, but that's only when like two threads are gonna come into like collision on who should go first, and then it's gonna pick the thread who has a higher priority set. But some languages like Python does not have set priority, so you're going to have to enforce your own priority system with like locks and semaphores. And that's it, guys. Thank you.
Because more than half of the full life cycle cost of a system is spent after the first version of the software is developed and released, modifiability is essential. That is why we want our design to be as easy to change as possible. The goal is to reduce the degree to which a change to a directly affected unit also affects the system other units. One of the tactics to do so is to be aware of the level of coupling in the system. The level of coupling among software units is the degree to which the units depend on each other. By lowering the coupling, we reduce the probability that a change to one unit will ripple into other units. We say that two models are tightly coupled when they depend a great deal on each other. Loosely coupled models have some independence, but their interconnections are weak. Uncoupled models have no interconnections at all. In actuality, it is unlikely that a system will be built of completely uncoupled models, because even when models might seem to be totally independent to each other, the context in which these are involved can directly couple them. Thus, Our goal is not necessarily to have complete independency among models, but rather to keep the degree of their coupling as long as possible. There are many ways that models can be dependent to each other. The reference made from one model to another. That is when a model A invokes operations in model B, so the model A depends on model B for completion of its function or process. The amount of data passed from one model to another. That is when a model A may pass a parameter, the contents of an array, or a block of data to model B. The amount of control that one model has over the other. That is when a model A may pass a control flag to model B. The value of the flag tells the model B the state of some resource or subsystem, which procedure to invoke, or whether to invoke a procedure at all. There are also different types of coupling. Some types of coupling are less desirable than others. The least desirable one is the content coupling. That is when one model actually modifies another. In such a case, the modified model is completely dependent on the modifying one. Although self-modifying code is an extremely powerful tool, you have to use it knowing the consequences. The resulting models are tightly coupled and cannot be designed or modified independently. The second one is common coupling. We can reduce the amount of coupling by organizing our design so that the data are accessible from a common data store. However, dependence still exists. Making a change to the common data means that to evaluate the effect of the change, we have to look at all modules that access to those data. With common coupling, it can be difficult to determine which model is responsible for having set a variable to a particular value. When one model passes parameter or return code to control the behavior of another model, we say there is control coupling between the two. It is impossible for the control model to function without some directions from the controlling model. If we employ a design with control coupling, it helps if we limit each model to be responsible for only one function or one activity. The most desirable ones are stamp and data coupling in that order. When complex data structures are passed between models, we say there is stamp coupling between these models. Only if data values and non-structured data is passed, then the models are connected by data coupling. Stamp coupling represents a more complex interface between models because the models have to agree on the data's format and organization. Thus, data coupling is simpler and less likely to be affected by changes in the data representation. That is why if coupling must exist between models, data coupling is the most desirable one. Another aspect to be aware of when speaking about modifiability is cohesion. In contrast to measuring the interdependency among multiple models, cohesion refers to the dependency within among a model's internal elements. The more cohesive a model is, the more closely related its pieces are, both to each other and to the model's singular purpose. A model that serves multiple purposes is at a greater risk of its elements needing to be involved in different ways or at different rates. For example, a model that encompasses both data and routines for displaying those data might change frequently and may grow in different directions. Instead of that, our design goal is to make each model as cohesive as possible so that each model is easier to understand and less likely to change. There are different types of cohesion. The worst degree of cohesion, coincidental, is found in a model whose parts are unrelated to each other. In this case, unrelated functions, processes, or data are combined in the same model for reasons of convenience. We say a model has a logical cohesion if its parts are related only by the logic structure of the code. For example, let's consider a template model of procedure that performs very different operations depending on the values of the parameter. Although the different operations have some cohesion in that they might share some program statements and code structure, this cohesion of code is weak compared to cohesion data, function, or purpose. It is likely that the different operations will evolve in different ways over time, and this will make the model increasingly difficult to understand and maintain. Sometimes a design is divided into models that represent the different phases of execution, like initialization, read, input, complete, printout, and cleanup. The cohesion in these models is temporal, in that the model's data and functions are related only because they are used at the same time in an execution. Such a design might lead into duplicate code, in which multiple models perform singular operations on key data structures. In this case, a change to the data structure will mandate a change to all of the models that access to that data structure. Often functions must be performed in a certain order. When functions are grouped together in a model to encapsulate the order of the execution, we say that the model is procedurally cohesive. Procedural cohesion is similar to temporal cohesion, with the added advantage that the function pertains to some related action or purpose. However, such a model appears cohesive only in the context of its use. Without knowing the model's context, it is hard for us to understand how and why models work, or to know how to modify it. Alternatively, we can associate certain functions because they operate the same dataset. For instance, unrelated data might be fed together because the data are collected from the same input sensor or with a single disk access. Models that are designed around datasets in this way are communicationally cohesive. The cure for communicational cohesion is placing each data element into its own model. Our ideal is functional cohesion, where two conditions hold. All elements essential to a single function are contained in one model, and all that model's elements are essential to the performance of that function. A functionally cohesive model performs only one function for which it is designed and nothing else. Every system has errors. This is why we should know how to treat them. An error is a situation that causes a system to deviate from its desired behavior. In order to take care of this, we have to include exception handling in the design, so the system addresses each exception in a satisfactory way and returns the system into an acceptable state. Some typical exceptions include failing to provide a service, providing the wrong service, corrupting data, violating a system's invariant, or deadlocking. A good way to check data problems that can help you handle data types exceptions is by identifying relationships or invariants that should hold among the data values and checking them regularly. Those checks can be embedded in the same code that manipulates the data. And talking about dependencies between models, these two important concepts come to light: scope of effect and scope of control. The scope of effect of a model is defined as all the models affected by a decision made by the model. The scope of control is the model itself and all its subordinates. There are those models it calls and all the models called by them, and so. The scope of effect of a model should be within the scope of control. All models affected by the outcome of a decision should be subordinate to the model that makes the decision. By analogy, the models on the top level of the hierarchy are the bosses. They make the decisions. The models in the lower levels are the workers. They receive instructions for bosses and carry out the work. The workers should not tell the bosses what to do. Violating the principle of scope of effect or scope of control might lead to duplicate decision making. For example, when a decision made by a subordinate model might have to be re-evaluated to the boss, increasing cultural copying, or content coupling. We use the term fan-in to refer to the number of units that use a particular software unit, and the term fan-out to refer to the number of units used by a software unit. In general, we want to minimize the number of units with a high fan-out. A high fan-out usually indicates that the software is doing too much and probably ought to be decomposed into smaller and simpler units. Thus, the left figure might be better than the right figure because its components have a lower fan-out. On the other hand, if several units perform similar functions, such as string searching, then we might prefer to combine them into a single, more general-purpose unit that can be used in place of any other original units. That kind of unit is likely to have a high fan-in. One of our goals in designing a system is to create a software unit with a high fan-in and a low fan-out. Fault and failure are two different terms that are important to distinguish. A fault is the result of a human error. The design fault can be propagated as incorrect code, incorrect instructions in the user manual, or incorrect test scripts. In this way, a single error can generate one or more faults in one or more development products. A failure, on the other hand, is an observable departure of the system from its required behavior. Failures can be discovered both before and after the system delivery because they can occur in testing as well as during operation. In some sense, faults and failures refer to invisible and visible flaws respectively. In other words, faults represent flaws that only developers see, whereas a failure are problems that the user or customer sees. It is important to realize that not every fault corresponds to a failure, since the conditions under which a fault manifests itself as an unobservable failure may never be met. So, how can we detect these faults? There are two principal ways to do it. The first one is passive fault detection. That is basically just waiting until a failure occurs during the execution and then tracking it to the fault that caused it. The second one is active fault detection. That is periodically checking for systems of faults or try to anticipate when a failure will occur. And for that we have several methods. One of them is identify an exception, as we already talked about previously. Another approach is to use some form of redundancy and then to check that the two techniques agree. The theory behind this approach is called inversion programming. If two functionally equivalent systems are designed by two different design teams at two different times using different techniques, the chance of the same fault occurring in both implementations is very small. Unfortunately, it has been proven that this is not as effective as we thought, because many designers learn to design in similar ways using similar design patterns and principles. Other method is diagnostic transactions. A second computer running in parallel is used to monitor the progress and health of the primary system. The second system interrogates the first, examining the system's data and processes, looking for signs that might indicate a problem. If the second system cannot directly examine the first system data or processes, it can instead initiate diagnostic transactions. This technique involves having a second system generate false but benign transactions in the first computer to determine if the first system is working properly. For example, the second computer system can open a communication channel into the first one to ensure that the first system still responds to such requests. Now that we know how to find a fault, we need to know how to correct them. For that, we have different methods too, like undoing transactions. That is when the system manages a series of actions as a single transaction that either executes in its entirety or whose partial effects are easily undone if a fault occurs midway through the transaction. Checkpoint or rollback. Periodically, the software records a checkpoint of its current state. If a system gets into trouble, it rolls its execution back to the recorded state and replies log transactions that occurred since the checkpoint. Backup. The system automatically substitutes the faulty unit with a backup unit. The backup unit is brought online only when a fault failure occurs, which means that the backup needs to be brought up to speed on the current state of the system. Degraded service. The system returns to a previous state, perhaps using checkpoints or rollbacks, and then offers some degraded version of the service. Correct and continue. If the monitoring software detects a problem data consistency or a stateless process, it might be easier to treat the symptoms rather to fix the fault. And the report, that is the most common one. The system returns to its previous state and reports the problem to the exception handling unit. Alternatively, the system might simply know the existence of the failure and record the state of the system at the time the failure occurred. And then it's up to the developers or maintainers to return to fix the problem later. The criticality of the system determines which tactic we choose. Sometimes it is desirable to stop the system's execution when a fault affects the system in some way, because it might be much easier to find the source of the problem if the system processing ceases abruptly on detecting a fault, and continuing may produce other critical effects. But other times, stopping the system's execution to a correct fault is too expensive, risky, or inconvenient. In that sense, the technique that we want to use to handle the faults is totally dependent on the system.
About reducing complexity, increased complexity is a byproduct of having a modifiable architecture. Unfortunately, this increase can have an adverse effect on product release and profits. So in order to reduce complexity, we can implement layered architecture. By doing so, this limits each component to interact only with its own or neighboring layer. So one example is the OSI model, which only interacts with layers above or below it. So by doing this, we make our code reusable, and especially when instantiating new family members in a layer. Next, we can use design by contract. This is an approach to documenting software which records the design process and encourages interaction between the developers. So this kind of allows for more brainstorming, bouncing off ideas off each other, which hopefully leads to more creativity and productivity. Each module has an interface that describes what said modules do, and this contract helps to form a clear and consistent method for testing and verification. We can also use prototyping. So this is basically where developers build a partially completed product, and developers and clients can examine the progress on the project. So these prototypes are important because you want to assess whether the current state of the design is aligned with the initial requirements. Here's where people can actually see it. They have a tangible product, and they can see whether they need to go back, do more revisions, look at the initial requirements, see if the project is progressing as intended. Next, we have fault tree analysis. So it's a method by which you look at a design and find faults that might lead to failure. And here on the right-hand side, you'll see an example of one of these fault trees. So we start by listing the possible failures of the design, and the failures are listed here in blue rectangles. So then we build a tree using AND and OR gates, which if you don't know about what those are, I'll explain them here in a moment. And these basically trace backwards through the design from the path of effect to cause. So instead of going top down, we're going to go backwards from bottom to top. So an AND gate means that both of these events have to cause failure. So password being exposed and a password not being changed, both of these have to be true in order for illegal access to be granted. And then with an OR, either one of these events here could be true. So either illegal access granted or a previous logout not being recognized. If either one of these events are true, then these could lead to a security breach. Next, we have design evaluation and validation. So we do this by measuring design quality. So one way is by looking at coupling, which is the indication of interdependence between modules in a design. So when you're working with a design, you want to create classes, modules, or objects that have some sort of dependence on other modules, because this allows you to see how they interact with each other, and what effect they might have on other modules. So by doing this, we can identify which modules are problematic and causing failure within your system. So next we're going to use design comparison. So using comparison tables for the different types of architectures of a system allows you to list the pros and cons. It also allows you to use some quantitative data to basically select or at least narrow down which kinds of architectures are going to be better suited for your design. So the first thing we're going to do is we're going to start by prioritizing the attributes of the design and how well they contribute to achieving the customer's requirements and needs. So here in this first column, you're going to see we have our attributes, and then we're going to give each one of those attributes a priority. And the priority is going to go from 1 through 5. And then we're going to go through and rank each of the architectures as they relate to each one of those attributes. So we have our 4 architectures, starting with share data and then going through pipe and filter. And 1 is going to be the least desirable, and 5 is going to be the most desirable in terms of ranking. So then you kind of go through and you do a little bit of math and you kind of compute these scores, and I'll show you here in a second how to do that. So what we're going to do is we're going to take one of these columns and we're going to multiply it by each one of the attributes priority. So we're going to do 1 times 1 plus 4 times 1 plus 3 times 4 plus 3 times 5 plus 5 times 1. That gives us a total score of 37. And then you just follow and do the same thing for each one of the architectures. So once you have all of these calculated, now here's where it helps you narrow down the design. Now this isn't to say that, the highest number here, which is going to be abstract data, is going to be the solution for your design, but it is going to give you some sort of insight as to which ones are going to be the best, or at least the most well suited. So for example, you could at least narrow down and say, abstract data types with the highest score, and then pipe and filter only being off by 2 points. These are probably going to be your 2 best options for a specific design, whereas you can kind of negate implicit invocation and shared data because they have the 2 lowest scores, and the scores kind of range. You can see the difference between them. Let's say 40 and 55 is 15, so you can kind of see there's a big difference, and implicit invocation and shared data are probably going to be less suited for your project. Now we are going to talk about design reviews. So design reviews have 2 different methods for evaluating quality. These reviews, it's kind of like a panel, and it includes several people from the architects, programmers, testers, and you even have moderators and recorders there. And 2 of the methods are going to be through validation and verification. So 1, we have validation, where you address the quality of the design, and then 2 being verification, where we ensure that the design is adhering to good design principles while satisfying the needs of the users. So we'll talk about validation first. So in validation, the architecture is demonstrated to ensure that it has the required structure, functionality, and characteristics specified in the requirements documents. So we go through and we trace the typical execution paths of the architecture to demonstrate the workflow. So it's kind of like a flow chart to see how the system is actually working. And we're also going to go through and find any error execution paths and trace those in the event of a system fault. So this kind of allows us to see where we might run into any sort of system fault and how to go back, revise those, and prevent them from happening. So we also have recorders and moderators there because they help resolve disputes and carry out any sort of revisions. And sometimes even, non-biased or third parties are actually brought in, to help with these decisions, because sometimes you might have two different groups of people that want different decisions for the design. So having a non-biased opinion again helps make a decision. And recorders and moderators are kind of there to lead the discussion, and take notes for any of the information that's going to be helpful going forward. And then in verification, we evaluate the quality of the design and the documentation and whether or not it adheres to good design principles. So this is just going through and really, asking ourselves, did we do what we intended to do? So some of the questions, and these are just 4 kind of key questions that you can ask, and obviously there's a lot more things that you can go over, but for example, we would ask, is the architecture modular? Is it well structured and easy to understand? Or can we improve the structure and understandability? We might also ask, is the architecture portable to other platforms, or are there any aspects that are reusable? So again, these are just kind of 4 key questions, not to say that there aren't many more that you can ask, but again, we're going back to see if our system that we've designed is to quality and basically adhering to the documentation that we first started, with our requirements document. So now we're going to talk a little bit more about design documentation for both customers and developers. So one key text is the software architecture document. And this holds all the information that's pertinent to all of the people involved in the design, from customers to developers, testers, and architects. The content depends heavily on how it will be used and who is going to be reading it. This text is really made to be a technical document used for quick queries for the design. The book itself is really rarely read from cover to cover because, there's going to be information that cater to different groups, and not everybody needs to read all of those different sections. So a customer isn't really going to need to go and see the kind of information that was going to relate to the actual programmers, because they might not even understand it to begin with. So for example, developers might use it for high-level language specifications, whereas customers could just read it for a system overview of the components and get that in natural language, as opposed to you having to read through code to understand it. And so here are just kind of the main components of the software architecture document. So first we have the system overview, and this provides an introductory description to the system. Next, we're going to have a list of the views, and each view provides information about the system structure from all of the different perspectives. So again, whether that's system architects, the developers, QA, testers, so on and so forth. So then we also have software units, which catalogs all of the modules that need to be developed and all of the interfaces that go with them. Next, we have analysis and data results, and these detail the system's architecture and computing resources and execution environments. Next, we have design rationale, which is the explanation and justification for the design. So in case anybody is wondering why you decided specifically on one design over another, here's where they would go, to kind of see an explanation of that. And then last, we have a definitions, glossary, acronyms section. So this is just kind of like a universal understanding for all the terms for everybody who's reading it, not just any of the technical developers. So this means that people like the customers can go in and, in case they don't just understand some of the terms, here's where you explain them, in simple terms so that they can understand it when reading through the document. And this slide here is just a list of references that were used for the presentation. The most important one here is going to be the textbook for the course, because here is where we obtained most of the information. So it's Software Engineering Theory and Practice, 4th edition, as published by Pearson. So this is going to conclude the presentation. So thank you very much for watching. We appreciate it, and we hope that you learned a lot. Thank you.